All right, so today we're going to embark in a new type of math that you have not seen in your previous math classes. Up until now, you've always been using what we call the Cartesian coordinate plane. It has the X and Y axis, and you're plotting points and graphing lines and parabolas. Today, we're going to introduce a different coordinate system. It's called the polar coordinate system. Instead of looking at a coordinate plane that has an X and a Y axis and has vertical and horizontal lines on it, what we have here is a polar coordinate system that is created by a plane that has a point at the pole. And what you might think of is it feels like it's just what the origin would be right here, but we don't call it the origin, it's called the pole. And then instead of thinking about how far left and right you go or how far up or down you go, you're looking at it like it's kind of like our unit circle. So right here, this positive x-axis is what we think of. And what we're looking at is how far out are you? So I have up to 5 rings out here. So that's called the radius, or how far out it'd be would be your R value. And then the other value that determines where you would plot a point is what the angle is. So we call this R theta. And so this particular point that I have plotted here, we would figure out what that is based on R, the radius, how far out it is. So if I count the rings, that's 1, 2, 3, 4 rings out. So this radius would be a 4. And the theta is what angle measurement it would be. And again, you're thinking in terms of the unit circle. So right here, you're at 0. You get up here to 90. And we end up right here at 135. Though most of the time we're going to be in radian measurement. So instead of 135, I'm going to call that a 3 pi over 4. And so instead of an x comma y, we have an r comma theta. And that's what we would call the polar coordinates. So let's practice plotting some points using that polar coordinate system. So this first one is kind of just a basic one. You have an R value of 3. So that means your radius is 3. I'm going to be 3 rings out. And I'm going to be at the angle 4 pi over 3. So 4 pi over 3 would be all the way around to here. And then I'm 3 rings out. 1, 2, 3. Right here. That's where that point would be. I'm going to go ahead and plot that point. I'm going to call it point P. Now that was kind of the easy version. Let's look at some other angles that we're familiar with how to plot, but will be just a little bit more challenging. So look at this next one. This one has a negative R value. Now that's actually something we haven't really talked about yet. And I've got a pi over 6. And then this one actually has a negative angle measurement. Now that we have dealt with. Okay, so let's start with Q. To have a negative R value means that you're still going to be 2 rings out, but you're going to be in the opposite direction of what you would typically be doing for that radius measurement. So what that means is I'm going to go to that pi over 6 mark. So I'm at this angle right here at pi over 6, but instead of going 2 rings this way, since my radius is negative, I'm actually going to go exactly opposite of that. So I land right there, actually, on that. So then I'm going to go ahead and mark that as point Q. All right, let's try one more. This last one has a radius of 5, so I'm going to be the 5th ring out, but the angle is a negative angle. Remember, that means you go backwards through your unit circle. Negative pi over 2 would land right here. So that's where my R value is, and so I'll put R right here. Okay, so those are the 3 points that I've plotted. Now, each of these coordinates designates exactly 1 point. Those are the only places, that was the only way I was going to do that correctly. But each of those points has more than one set of coordinates that I could write. So in other words, if I were to work through this backwards, instead of me giving you the ordered pair and asking you to plot it, what if it was the other way around? What if I gave you the plotted point and asked you to give me the coordinates? Well, I could have given you this coordinate, but I could have used these other features and given you different coordinates that still landed there. Could have used a negative r, could have used a negative angle, could have used a negative r and a negative angle. There would be different ways to land at each one of these spots. So that's what I want to work on. Now, in all honesty, there'd be an infinite number of coordinate sets that I could create, but I'm going to limit us here. I'm going to go from negative 2 pi to 2 pi. That's what I'm going to limit us out at, meaning that your angle that you create for these three angle measurements, you could go anywhere from a negative 2 pi, so one full revolution backwards, all the way to a positive revolution too. So that's really two full revolutions that I get to pull from to come up with ways of landing in these spots. So let's just start with a P. So with P, I want to land right here. So we got to think of another way to land there. And so one way would be to look at it and try to get a negative R value. Well, if I'm going to use the negative R value, that's going to shoot me backwards through that, then I have to come back up here and I have to use this angle. So I would use this angle, but use a negative R, which would take me there. Well, this angle is a pi over 3. So another way to write this would be to say a negative 3 with a pi over 3 angle, right? So one more time, that means that would take you to your pi over 3, but the negative 3 would make you shoot backwards through there and land you right there. So this is an alternative set of coordinates to this. All right, let's try another set. I could, instead of the negative R, what if I used a negative angle? So that means backing up this way. So how much did we just back up to get to there? Now, there's different ways you can think through that. In my head, I guess I always think, well, I backed up a quadrant and a little bit more. And I think in my head, well, a quadrant and a little bit more is a 2 pi over 3. So what I just did is I backed up 2 pi over 3. So that's my way of thinking through it. There's other ways. But what I'm saying is that I would use a negative 2 pi over 3. Now, when I did that, I truly landed exactly where I wanted to land. So I don't want to goof up my R value. I'm going to keep my R value as a positive 3 because the angle took me to where I wanted to go. I don't need to change the R value. All right, so now a third option could be to make both the R and the theta negative. So you can make them both positive. You can make one negative, you can make the other negative, or you can make them both negative. So ultimately, what I'm shooting for here, and I'm going to draw this in, I need to land either here or I need to land up here. Those are the two spots that I can land. If I land down here in the bottom left, then I would keep a positive R value because I'm where I want to be. If I land up here, I would use a negative R value to shoot it down to where I want it to be. Okay, so I have landed at point P with this angle and this angle. I need to be able to land this spot up here one more time. I did right here. I have to land there with a negative angle. This is getting kind of messy. Sorry. This one maybe is a practice one, just thinking through the process on this. So I have to back up all the way to there, and then I have to use a negative R value to take me to there. All right, so how much is that backing up, do you think? What degree would that be? Right, so in my head, I'm going 1, 2, 3 quadrants, and then I'm at the next spot. So 3 quadrants and the next spot is 5 pi over 3. All right, so my angle is a negative 5 pi over 3. And since I'm not really where I want it to be, I have to make my 3 negative to shoot it backwards through there. Okay, let me clean this up a little bit. Get rid of, oops, it's not going to let me erase. That's going to be problematic. In the erasing, yes, there it is. Okay, so we did P. I'm going to get rid of P. Let's try Q. All right, here we go. So you're going to do 2 negative angles. You're going to do 2 positive angles. They already gave me one of the positive angles. So one of the positive angles And this is a radius of 2. One of the positive angles was here, but then the negative r took me down there. What if I just did a positive angle and got there with a positive angle? What would that angle be? The 7 pi over 6. And since you're landing exactly where you want to land, then you leave your r value positive. Okay, so now let's try to land there with some negative angles. Okay, I could just back up that much. What would that angle be if I backed up to there? In negative 5 pi over 6. And since I'm backing up and I'm landing where I want, then I leave that r value positive. Okay, so then my last scenario is to back up again because I need another negative angle. But I'm gonna land it all the way to over here to where it's straight across. And then I'm also going to use a negative r value to shoot me down where I want to go. So then what is this negative angle that would take me all the way to there? Heck, I almost went all the way around. That would be a negative 11 pi over 6. And since it's not really where I wanted to land, I need the negative 2 to take me through to where I want. Okay, what I'd like you to do is pause the video and try to do R for me now. Can you find the missing coordinates for R? So take a minute, pause the video, try it on your own. All right, so here I'm going to go through it now. Let's check you. I've already used one of the negative angles. So what I'm going to do is, in no particular order here, it doesn't really matter. I know I'm going to be 5 rings out. I know that I'm either going to have to land here with the positive R, or I'm going to have to land here and use the negative R to get me down there. Okay, so, and by R, I mean this R, not this R. Okay, so here we go. I think the easy one would be to land here. That's an easy pi over 2, positive pi over 2. But since it's not where I want it to be, oops, I'm going to use a negative on my R value. So it's going to look like that. Feels like I'm writing this coordinate backwards because I'm starting with the theta, just sort of to get your mind. Once you get used to it, you'll probably write your R value first. But all right, so I landed right here, made my R value negative. All right, I'm going to keep on going. What if I kept on going down to there? What's that angle? Keeping it positive, it'd be a 3 pi over 2. And you're actually landing where you want to, so you keep your R value positive also. Okay, last scenario would be to use a negative angle with a negative R. So my negative angle, taking it all the way up to here, is a negative 3 pi over 2 with the negative R value with it. So negative 5, negative 3 pi over 2. All right, hopefully that's making sense for you. Let's keep going. All right, so I said that this is a whole new coordinate system, but that doesn't mean we don't still have some commonalities between the rectangular coordinate system that you're used to with x's and y's and this new polar coordinate system. All right, so what we're looking for here today is like, how do these two ideas connect? So I know we call this now the pole, but if I'm in rectangular coordinate system, I call it the origin. And so with our new method, we're looking at how far are we wrapping around the unit circle, and we're looking at how far out are we going. There's your R and your theta. But when I plot a point, I can also think of it as how far over and how far up am I going. So that would be an X and a Y. And lo and behold, look at that. There's a right triangle I just created. So what we'd like to do is kind of brainstorm with this right triangle. I've got an X, I've got a Y, I've got an R, I've got a theta. I'm looking for some sort of a relationship, an equation, ultimately, that I could write using X, Y, R, theta. So take a minute and look at that and say, all right, what sort of relationship do we know from that? All right, I think probably the first one, okay, so here's what I'm going to do. I'm going to go through some, but I don't really want to write them in this yellow box until we've cleaned it up. So I'm going to write them over here. Maybe you just watch. You don't even need to write these. But I think the one that jumps out at me is just an x squared plus a y squared equals a r squared. Just a little Pythagorean theorem there. That would work. Okay. The other thing that would jump out at me would be, well, with a right triangle, we can do a lot of SOHCAHTOA. So let's start looking at our SOHCAHTOA options. I could do from theta, I could say that the sine of theta would be opposite over hypotenuse. I could say the cosine of theta would be the adjacent over the hypotenuse. I could say the tangent of theta is opposite over adjacent. All right. And really, those are the four rules I want. But I want to sort of rearrange them. And so when I write them in the yellow box, now you can write with me. I kind of want to, like on one side, I want to have the rectangular coordinate systems or coordinate values, so the x and y on one side, and I'd like my r's and thetas on the other side. So keeping kind of separating those. So I'm going to do this in a particular order. So I'm going to look at these two first of all, because they're the ones that really aren't set up like I like. Now, this one has the x's and y's on one side, the r on the other. Perfect. This one has the theta on one side, has the x and y together. So rectangular, polar, rectangular, polar. Those are ideal. These are not, because I've got the y and the r. So what I'm going to do here is I'm going to move this r over to the other side so that it's with the theta. So I'm just going to take it times r over here. Same thing with this one. I'm going to take it times r and move it over here. So the order that I'm going to write them, first one I'm going to write is this one right here. I'm going to move the r to the other side, and when I do that, the x will be isolated, and x will actually equal r cosine theta. And then I'm going to do this one. When I move the r to the other side, the y will be isolated, and it will be r sine theta. All right, now the other two, I guess what I want you to notice here is in these first two, you have both the r and the theta, but then you only have one rectangular value. These other two go the other direction. I'm going to have two rectangular values, got the x and the y, but only one polar value. Got the x and the y, but only one polar value. Okay, so then I'm going to go ahead and I'll do, let's do x squared plus y squared is going to, oh, you know what? I'm going to change that, sorry. I'm going to go ahead, just like I did up above, I had the isolated term. I'm going to put the r squared first. R squared is equal to x squared plus y squared. And then I'm going to say the tangent of theta is equal to y over x. So the first two are going to kind of work together, and the second two are going to kind of work together. Now, I do have a big sticky note. I got the nice frame. You need to know these four rules. Now, they're not rocket science. This is stuff we've been doing, but you've got to kind of know them without having to go back to drawing the triangle to know them. Okay, so for the rest of this lesson, what we're doing is we're just going to use those four rules and practice moving left and right. I'm sorry, practice moving from polar to rectangular and vice versa. So looking at this first one, this isn't polar, this is a polar coordinate. This is your r, this is your theta. So since I know r and I know theta, what I'm trying to do here is I'm trying to turn that into an x and a y. So since I already know the r and the theta, I want to use the rules that have an r and a theta. That's going to be these first two right here. And why don't I go ahead and do that? X is going to equal, and just for the sake of our notes, I'm going to go ahead and write this until we get a little bit more familiar with it. Okay, so x equals r cosine theta, and so then we're going to fill it in. It's going to be 2 cosine of pi. And I know the cosine of pi. The cosine of pi is -1. So x actually ends up being a -2. Then we have to do the same thing. Boy, I didn't leave myself much room to work here. So now I'm going to do a y equals r sine theta. So let's fill in our r and our theta. Y is equal to 2 sine of pi. But I know that the sine of pi is 0. So y is just 0. Okay, now I started with this one because I feel like we can make this make sense in our head. If you think of this in the rectangular coordinate system, and to be honest, I really would probably come back and I would write this as an ordered pair, -2, 0. That would be your final answer. And I could plot -2, 0. It would land right here. But hopefully you also understand how this would work as polar coordinates. I'm 2 rings out and I'm over at pi. So if I did have the rings drawn, 1, 2, I would be 2 rings out and I would be at pi and it would land in that same spot. So these two are equivalent coordinates then, just in different formats. Okay, so now we're going to try this one more time. Actually, I'm going to turn you loose. Can you do the same thing? A little bit trickier. Got to know your unit circle stuff. Can you turn this 4 pi over 3 into an x, y? Pause the video. All right, here I go. X equals, and this time, since we've already done it once, I'm going to go ahead and just jump right in. X equals r cosine pi over 3. Y is going to equal x sine pi over 3. The cosine at pi over 3 is 1/2, while the sine at pi over 3 is √3 over 2. So x is going to equal 2. Y is going to be, think of this as a 4 over 1. The 2 and the 4 could reduce. You'd have 2 √3. Final answer, write it as an ordered pair, 2 comma 2 √3. And that is the rectangle. That's us converting points, ordered pairs. Now it's going to get fancier. Right now, that was just converting points. Let's look at something different. Could you convert your points that are rectangular and convert them back to polar? All right, so now what you're doing is you're using the other two rules. I'm going to be using these two rules because this time I know my x and my y, so I want to use the rules that have the x and the y in it. So here we go. I'm going to have a -1 squared plus a 1 squared equals my r squared. So that's really just 1 plus 1. So r is going to equal the square root of 2. Now remember that sometimes r can be negative. All right, well, that's where when you do the square root, you might do a plus or minus. But typically the way we're going to do this is we're going to keep our r value positive when we do this. We're going to keep it as simple as we can. So don't put that plus or minus on there. You keep it positive. Okay, the other thing that I'm going to do is the second rule where you do the tangent of theta is going to equal your y over your x. Okay, well, that just reduces to -1, and I'm lucky enough to have that fall on the unit circle here. So when is tangent going to be -1? And you should know that that's going to happen in your second and your fourth quadrant. So you know that your answer, your theta, could be up here, but it could also be down here. So which one do I write? Well, I write the one that corresponds to the original. So it is worth noting right now, next time I'm going to do it first, but right now you should recognize you went left and you went up. This is a quadrant 2 angle. So when I'm looking at this, I want my quadrant 2 angle. So only write one answer. Theta is going to be 3 pi over 4. All right, so your final answer, though, we're going to write as an ordered pair. It's going to be root 2, comma, 3 pi over 4. All right, pause the video. You try the next one. All right, are you pausing the video or are you just waiting me out? I don't care. You do you. All right, so here we go. I know my x and I know my y. So I'm going to do 0 squared plus negative 2 squared equals my r squared. So 0 plus 4. Oh, this came out nice. R is going to be 2. Got it. Next, I'm going to say tangent of theta is equal to the y over the x. Oh, wait a minute. That's going to be undefined. Tangent is undefined in 2 different places. But the original problem up here, think about what quadrant that's in. You're over 0, down 2. That is straight down. So it's not really a quadrant in a quadrant. It's on the axis. And so that would actually happen at 3 pi over 2. And again, we are doing radians as much as we can. The only time I would do degrees is if they were giving me something in degrees. So R value is 2, theta is 3 pi over 2. Keeping everything positive here, not going with negative or R's or negative thetas. All right, so there we were converting points. Now we're going to try converting equations. So in the same way, you could have a line or a parabola or an exponential in rectangular coordinates. What we're looking at is converting that idea into polar coordinates. So this one right here is 2x minus 3y equals 5. So that's a nice rectangular coordinate system. I'm going to change it so that it looks like a polar, as polar values. So instead of using x's and y's, I'm going to replace my x's and y's with r's and thetas. So looking back at your previous 4 rules, I know my rules, so I don't need the chart anymore, but you can still peek back if you need to. The x, I'm going to replace it with what x is the same as. And x is actually equal to r cosine theta minus 3. And then instead of a y, I'm going to write r sine theta equals 5. All right, so that's really what you do. You just trade it out. Now, there is kind of a proper way to write polar equations. And just like in rectangular system, we like them to be y equals, and your calculator forces you to do y equals. Okay, same thing here. Polar coordinates or polar equations are typically written with an r equals. So what I need to do here is get my r isolated on one side, everything else on the other. That's a little bit tricky because the r is caught up here, but I have a different r caught up here. These are not really like terms that I combine, but what I can do is that r and that r, I could factor that out of there, and that's what I'm going to do. Let's factor out the r, and then what I'm going to have left is 2 cosine theta minus 3 sine theta equals 5. And remember, my whole goal is just to isolate the r. And since that's being multiplied right there, I'm just going to divide both sides by that big old set of parentheses, and I'm going to be done. It's not going to look pretty, but it's got the r isolated. 2 cosine theta minus 3 sine theta. Now, the original was a line. I know that was in standard form, a line. If I were to graph this equation, and we're going to talk more about graphing later on, but if I were to graph this, it would still look like this same line. Again, we'll talk about that later. Let's take a look at this next one. It's the other way around. It has an r and a theta in it. So this is a polar equation. I don't know yet what this would look like on a graph, but I'm just really trying to rearrange it and turn it into a rectangular graph or equation. So the first thing that jumps out at me on this one that I don't love is that secant. So I would probably, now we have definite strategies, so I'm kind of purposefully doing one of each type. So you're going to want to keep your notes handy so that you can see. That's what you do with a linear situation. It kind of always plays out the same way. This one, when you have a secant, maybe a cosecant, the first thing you want to do is go ahead and get that into sines and cosines like we're more familiar with and like our four rules use. Okay, so now the next thing that I don't love, by doing that, I've created a fraction for myself. So I can fix that. I'm going to go ahead and take both sides times my denominator. So then what I have is r cosine theta equals 4. So that's a better scenario. I'm using cosine instead of secant. I don't have fractions. And I'm hoping that soon you will look at that and you'll say, well, heck, r cosine theta, isn't r cosine theta just x? And all of a sudden, you have that converted. This is a vertical line. So what that means is this original one up here, if I were to graph that on my polar graph, it would graph as a vertical line as well. Right, so converts very nicely to this pretty simple little equation right here. But you got to go through these steps to get it to that point. All right, here's another one. Now this one is different. It is in polar form, trying to go to rectangular because I've got the r and theta, but this is different than my last one because it's already got sine, it's not a fraction, and somehow or the other I've got to get this turned into an x and a y. All right, so this one, the strategy we want to use, I sure wish that this r in this one was squared, because if you think of your formula, if you look back at your four rules, you have this right here as one of your rules. So if I could get this to be an r squared, then I could replace it with an x squared plus a y squared. Now, there's two ways that you can turn this r into an r squared, and that would be by squaring both sides, but that's not the one I want. What would be another way to turn this into an r squared? Did you say take it times r? Okay, all right, that's what I'll do. I'll take both sides times r. That's what you have to do. Make note of it, show it right there so you know what you did, because this is now going to turn into r squared. And this, the way that I probably would write that is I'd go ahead and write the 8r sine theta like this. Now, I did what I wanted to get this to be an r squared, so now I'm replacing it with an x squared plus y squared. But I also need to get rid of this r, and I need to somehow turn it into an x and y. And what I'm hoping, again, eventually, you'll notice right here, we have an r sine theta. And r sine theta is just a y. Okay, so we've done the converting. Now the rearranging is what we need to do. And this one, if you'll notice, okay, I'm going to a rectangular equation. Do you know what this would graph like? This is something, I mean, it's a rectangular one. We've done lots of rectangular stuff through the years. What would this thing graph like? Yes, it would be a circle. Good answer. This is going to be a circle because you've got your x squared and your y squared. Now, to make this look like a circle, though, so I'm coming over here to the side, here's what a circle equation looks like. This takes us back to, well, you've done circles several years, but this was maybe the last time you would have done it was with conics, or maybe you remember doing it a little bit earlier in this year, but that might be a stretch. I don't know. But this is what you're shooting for. This is what we want our equation to look like. All right, so it doesn't really look like that. And so what I need to do is I need to subtract my 8y over. So it's going to look like this. X squared plus y squared minus 8y. And I should have told you to write little here because this is a kind of a longer problem. What we have to do to get this equation into this format is complete the square. This is what you would have done in college algebra. You would have had something like this that you would have had to complete the square to get it into this format so you could graph it. So let's refresh our memory on completing the square. I went ahead and kind of hinted at you're going to subtract your 8y, and then we kind of do this plus something equals, and now it equals 0 because we brought the 8y over. Okay, so the idea is that you are completing the square with the y's. The x you don't have to complete the square with. To complete the square, you take half of the 8, which is 4, negative 4, and you square it, which is going to get you a positive 16. So you put a plus 16 right here. But by putting a plus 16 on the left, you got to keep it balanced. You're going to put a plus 16 on the right. This is now x squared plus. The point of completing the square is because that will always factor to a binomial squared so that it's going to look like this over here, like we want it to. So it's going to be a y match this sign right here. So it's going to be a minus. And the value that we squared was a 4 equals 16. And that is the equation. We're done at that stage right there. But do you know how to graph that? All right, so let's go on ahead and keep reviewing that part of it. Your center of your circle is your H and your K. Now, in this case, the H isn't really there, so it must have been a 0. And then the K, and notice these are subtractions. So if it is a subtraction, you keep that. It's just a positive 4. You always do the opposite, remember, when you're inside parentheses. So a minus is actually going to create a positive when you do your center. Your radius, notice that it's going to equal the radius squared. So your radius would be 4. And this graph then be over 0, up 4. So you'd be up here. And then you'd have a radius of 4. So your circle would look something like this. And if you were to have graphed this original one on the polar graphing system, it would have looked like this also. So sometimes polar equations are nicer, sometimes rectangular are nicer. This would be an example where I feel like the polar version of a circle is a lot cleaner looking than what the rectangular version is. Okay, that's kind of it for today. I'm going to keep going one more thing. I told you that we were going to look at some more graphing later on, and we need to do a little bit of prep work to get us ready for that tomorrow. So we've done this before. What I'm really needing is a great big table of values. So we split up the work and everybody gets some angles. And so I'm going to ask you to pick an angle, something divisible by 10, somewhere between a 0 and 360. So I'm going to degrees for right now. And so let's pretend that you picked a 50-degree angle, let's say. Okay, so if it's 50 degrees, now what you can do is you can convert your 50 degrees then into radians by taking it times pi over 180. And that's going to get you your radian value. So I'm going to do my 50. I should have had this done already, sorry. All right. As a radian measurement, that's a 0.87, and I'll say 3. Okay, now, you can use the 50, you can use the 0.873. You just have to make sure that your calculator is in the right mode. All right, so I'm going to guess I'm going to go ahead and I'm just going to do the degree measurement and check my mode and make sure that it's in degrees. It is. Okay, so now to calculate this, I'm going to take my 50 degrees and I'm going to put it right here. Now, what this is saying is that I'm going to take 3 times 50, Well, 3 times 50 is really a 150. And so I'm going to do 5 times the cosine of 150. Now, I know that the cosine of 150 is on my unit circle, but really what I'm needing are decimal values. So I'm going to let you off the hook on having to evaluate your unit circle. I'm just going to type this in, 5 cosine of 150. And I get a negative 4 point. And to be honest, if you went to the tenths place, that's going to be highly sufficient for what we're doing. Okay, now I'm going to try my 50 degrees right here. So it's going to be a 1 minus 3 sine of 50. And I'm just going to type in my calculator, 1 minus 3 sine 50, and I get a negative 1.3. Okay, so what I'm needing you to do is maybe like 3 angles for me. So I just did 50 for you. That's great. Pick a couple other, maybe, and make sure it's divisible by 10. Something from 0 to 360. Fill in this chart. And then work on your homework, and we will reconvene tomorrow looking at graphs. All right, good luck.